Hi and welcome to part 4 of my video playlist about the preparation of benzonitriles. In this video I'll show you some strategies for the cyanation of unsubstituted arenes. Like amoxidations, this is not a very selective reaction and may require some optimization. For certain types of aromatic nitriles, though, this approach can be practical and valuable. One strategy is the treatment of electron-rich arenes with electrophilic cyanide cation equivalents and Lewis acids. Cyanogen halides are sometimes used, but these are also good halogenating reagents and tend to yield aryl halides as byproducts. Aryl cyanates, thiocyanates, and compounds with a nitrogen-bound cyano group often give better results, but are more expensive than cyanogen halides. If a given arene is too unreactive, or if the desired regioselectivity cannot be achieved with an unsubstituted arene, a polar organometallic may be used as nucleophile instead. These can be generated by direct metallation or from an aryl halide. Some oxidized noble transition metals are sufficiently strong oxidants to metallate unsubstituted arenes directly, in particular if a chelate complex can be formed. This enables catalytic oxidative cyanations, but again, regioselectivity can be an issue. I'll show you now some specific examples of each of these three strategies, so you get an idea about the scope and the required reaction conditions. This here is the direct Friedel-Crafts type cyanation of biphenyl with cyanogen chloride. A good yield of only one regioisomer resulted, but unfortunately the scope of this reaction is limited and few successful examples have been reported. Phenols react with cyanogen halides at oxygen, but direct cyanation at carbon can be achieved with thiocyanates and Lewis acids. In this example, a combination of methyl thiocyanate, aluminum chloride and boron trifluoride etherate brought about a highly regioselective cyanation of metacresol. Also anilines can react this way. Methyl isocyanate, by the way, is not a gas, but a liquid that boils at 131 degrees Celsius and thus easy to handle. Compared to Friedel-Crafts acylations, electrophilic cyanations have a higher tendency to yield isomeric mixtures. When toluene is acylated with acetyl chloride, for instance, over 90% of 4-methylacetophenone is usually obtained. With phenylcyanate, however, an almost equimolar mixture of ortho- and para-methyl benzonitriles resulted. Thus, it must be checked case by case if direct electrophilic cyanation is a viable option for a given target nitrile. These regioselectivity issues can sometimes be solved by using a polar organometallic of defined structure as nucleophile. In this example, dibromoanisole could be selectively orthometallated with isopropyl magnesium chloride. Reaction of this Grignard reagent with an N-cyanosulfonamide gave the expected nitrile. The required electrophilic cyanating reagent was prepared in one step from phenylurea and tosyl chloride, as shown here. Another group of cyanide cation equivalents are dialkylated melanonitriles. Unfortunately, these reagents cannot be prepared from ketones and cyanide, but only by alkylation of melononitrile or from other malonic acid derivatives, what makes them rather expensive. These reagents can transfer a cyano group to polar organometallics, with an alpha-metallated nitrile acting as leaving group. Here, for instance, a lithiated arene was converted into nitrile in high yield by treatment with dimethyl melononitrile. Nitriles can also react with polar organometallics to yield ketones, what can lead to product mixtures when using these melanonitriles. If the electrophilic cyanide equivalent is added to a polar organometallic reagent too slowly, the nucleophile may also react with the newly formed nitrile and yield an unwanted ketone or imine. And in the case of halogenated arenes, the leaving group may act as nucleophile and give still more byproducts, as in the last equation on this slide. Polar organometallics containing halides are dangerous, however, and should better be avoided altogether. Fewer unexpected products are formed with tosyl cyanide as electrophile. In this example, a pyridyl Grignard reagent cleanly reacted with tosyl cyanide and gave a high yield of the target nitrile. Interestingly, the reactions were conducted in dichloromethane, not a common solvent for polar organometallics. A similar reaction was achieved with N-cyanobenzimidazole, as shown here, but the yield was not as high as in the previous example. The third strategy is based on the electrophilic palladation of arenes by palladium-2 complexes. In order to exchange hydride by cyanide and reoxidize palladium-0 to palladium-2, stoichiometric amounts of some oxidant are required. Some academic researchers use silver-1, but copper-2 or other oxidants do also work. In many of the reported examples, a number of additives and ligands are used, what complicates the optimization of such reactions and the purification of the product. These reactions work best if a chelate can be formed during the metallation, as for instance with 2-phenylpyridine. Unfortunately, this severely limits the scope of target nitriles. In this example, the cyano group was formed by amoxidation of the solvent DMF, and the arylation step was a Heck-type addition of the aryl palladium intermediate to an imine, as sketched here. This here is a rare example of the oxidative cyanation of a non-chelate-forming phenyl group. A substituted quinoline and acetylglycine were required as ligands, and reoxidation of palladium was achieved with a large excess of silver fluoride. A mixture of regioisomers resulted. Terzbutyl isonitrile can also be used as cyanide cation equivalent. Here an indole was cyanated with this reagent at the highly nucleophilic position 3, and as oxidant just one equivalent of copper trifluoroacetate was used. Instead of palladium, also cobalt complexes can catalyze the electrophilic cyanation of certain chelate-forming arenes. N-cyanosuccinimide was used both as electrophilic cyanide source and as oxidant in this example. Still, 40% of silver-1 was also required to attain a good yield. In this example, an electron-rich arene was cyanated by intermediate electrophilic iodination. The cyano group was again generated by copper-mediated amoxidation of DMF. This is one of the many recently published procedures in which ammonia is mixed with iodide under oxidizing conditions. As discussed in the third video of this playlist, this is extremely dangerous. The shock-sensitive explosive nitrogen triiodide can be formed here and sublime and crystallize in the upper part of the reactor. This is another one of these dangerous procedures which I cannot really recommend. There are plenty of inexpensive cyanide sources, and there's no need to use DMF for this purpose. In this example, a large excess of AIBN provided the required cyanide. No noble metal, but only a slight excess of copper acetate brought about a high-yielding electrophilic cyanation. This chemistry was again limited to chelate-forming 2-aryl pyridines. One special type of oxidative cyanation is the introduction of cyano groups at positions 2 of pyridines. In general, pyridinium salts with a leaving group at nitrogen can react with nucleophiles at positions 2 or 4 and then undergo elimination of the leaving group, as sketched here. Pyridine N oxides do not usually react this way, but if the negative charge at oxygen is removed by alkylation, acylation or sulfonylation, then this substitution can proceed smoothly. If positions 2 and 4 are both unsubstituted, mixtures of regioisomers often result. Here, for instance, a pyridine N oxide was first methylated at oxygen with neat dimethyl sulfate and then treated with a slight excess of aqueous sodium cyanide at room temperature. A high yield of the 2-cyanopyridine was obtained. Fortunately, the first step proceeded with high selectivity, without any competing alkylation of the amide, despite the vigorous conditions required for this methylation. Even halogenated pyridines will preferentially add cyanide at the unsubstituted positions. Here, for instance, despite the excess of cyanide, a high yield of 2-cyano-6-bromopyridine was obtained. Stopping the reaction with cyanide after only 20 minutes at 0 degrees Celsius prevented the substitution of bromide. In this example, pyridine was activated by a sterically demanding leaving group at nitrogen. This enabled a clean cyanation at position 4. Also unsubstituted 1-alkoxypyridinium salts mainly yield 4 cyanopyridines when treated with cyanide, but the yields are lower than in this example. By the way, when mixing pyridine with bromine or chlorine, no reaction occurs, and no 1-halopyridinium halides are formed. That's a pity, because these could be interesting intermediates for the preparation of substituted pyridines. Another sophisticated way of activating pyridines is acylation with a mesylate of chlorinated oximes, as shown here. In this example, the starting pyridine contained a heteroaromatic aldehyde, which remained unchanged, however, during the cyanation reaction. Concerning potential side reactions, there are just too many to discuss here. As mentioned, cyanogen halides are also good halogenating reagents, what is one of the main reasons for their limited use in electrophilic cyanations. Here, for instance, reaction of an electron-rich arene with just one equivalent of cyanogen bromide at room temperature only yielded a mixture of the brominated arene and a dimer formed by single electron oxidation. Interesting, but not very useful. Here are some more references which you can also find in the description of this video, including some dangerous iodine-mediated ammoxidations which I would rather not try out. The next and last video of this playlist is about the conversion of other benzoic acid derivatives into nitriles. These include trihalomethanes, carboxylic acids, amides, acyl halides and esters. See you then.